Okay, in this lesson, we're going to talk about the ideal gas law, looking through our notes. So what does it mean if something is known as ideal? So that's going to be our focal point. So we're going to focus in on these ideal gases that go according to our KMT, or a kinetic molecular theory for it. So with the ideal gas law, we will be completing math for this one. You will need your calculator for today's lesson for it. Now, you might have to check back for the example 1, 2, and 3 to check your answers for it. This is just going through the notes. So, does gas have mass? So, this video is linked for it, and this guy gets so super excited about does gas have mass? And yes, it does. Even though it has an insignificant volume and no definite shape, gas has mass, and we can see it simply with two balloons. If we put them on a ruler like so, you can see that if one has more air than the other, or a lighter gas, it would tilt our ruler for it. So let's talk about gases. Some assumptions that we're going to use with our ideal gas law is that they're going to follow that KMT, kinetic molecular theory. No attraction, insignificant volume and shape, and the perfectly elastic collisions, aka hitting, bouncing off of one another, and moving in straight lines as they go. So with the three named gas laws, the amount of gas was kept constant, but what if I told you you can change the amount of gas? So this is a new equation alert. And when we start to say that we're changing the amount of gas, we're starting to look that we might have mass and moles come in for it. So our equation for the ideal gas law is PV equals nRT. So pressure, volume, and temperature we've already looked at, PV and T. We're now adding the amount of gas as N, and we're going to add a constant as R for it. So, did you miss us? Keep calm and calculate moles. So when we look at N, that's going to equal the number of moles we have for it to keep it consistent there. So if we're looking at the ideal gas law, we have PV equals nRT. Let's go through each of the letters, and we'll see that P is the pressure measured in kPa, or we could have it in ATM too. In class, we're going to exclusively work with kPa. V is going to be our volume and has to be measured in liters. N is our number of moles and will be measured in moles. Sometimes you'll even see it as MOL. So if we're given grams, we're going to have to do a conversion to moles for it. Then we have our R, which is our gas constant, which is going to be 8.314. And we'll look at how we got that gas constant momentarily. And then T is going to be our temperature, always measured in Kelvin. So if you're given Celsius, don't forget to add 273 to it to put it in Kelvin, because remember, Kelvin's an absolute scale, so we won't have any negative answers for it. So Avogadro's principle. Remember Avogadro's? He was talking about moles and atoms. He also worked with molar volume, and it's in its name. We're looking at the molar volume, or moles with our liters. So what he actually found, that 1 mole of any ideal gas is actually equivalent to 22.4 liters. Now, it has to be at what we talked about earlier in our lessons, STP, meaning standard temperature and pressure. So when we're talking about the ideal gas law and how we got the R value, we're looking at the data of all these gases. No matter what their mass was or how many atoms they had, they were all so close that they averaged out to this 22.41. So how did they come up with the gas constant, that R value? Well, they used this knowledge of the molar volume, that 22.4, and then they did it at our standard temperature and pressure. And they solved for the unknown variable within. So if we have PV equals nRT, we can prove our R constant because we have our standard pressure here, we have our molar volume here, we have our number of moles is equivalent to 1 mole. We're solving for our R, and then we have our standard temperature here. Now remember, standard temperature has to be in Kelvin. So they took that 0 degrees Celsius and they added 273 to it. So that's how they solved for ATM to be 0.082. to 1. Now, if we were doing it for kPa, that's how we would get that 8.314. So the same way that they came up with the R constant is the same way we're going to be able to solve for different variables. So tips for solving ideal gas law problems. Locate all the variables, aka the numbers. So we have PV equals N, R, and T. We have 5 variables, so at least 4 of them have to be given to us. You can make a list, you can write it underneath as we go through it. Then you're going to plug in each of your numbers with its units in the correct spot. Then I would solve each side and then solve for the unknown for it. So what that means, if we had 2x equals 6, to get x by itself, we would divide both sides by 2, and then we would find that x is 3. So that's how we're going to solve our ideal gas law problems for it. So thanks for watching through the basics of the equation and then how to get the R value and eventually solving for it. Have a good day.